Hello, I'm Bill Anderson. Welcome to a course on linear static finite element analysis. Most of our work will be on structures, but toward the end we'll talk a little about heat conduction also. In this introduction, we'll do a course overview, then a personal introduction, then talk a little about the foundations of finite elements, the historical review, and some definitions. I'll end up with a list of commercial codes that are available. Let's do an overview of the course. Three goals that are important for us are to understand the finite element theory, then to apply that in modeling structural systems, and thirdly to become familiar with commercial codes and the tremendous capability in these codes. How can we do this? Well, my approach is to give lectures and then laboratory sessions and case studies. In fact, my favorite approach would be to have all three of those for each of the finite elements that is to be considered. For instance, a solid element. I would prefer to have a lecture on that than a laboratory session and a case study. This would round out the viewer's knowledge about the area. Now, the typical viewer of this material will be an engineer, but I'd like also to encourage people that are in the physical sciences and in mathematics, including computer science, because you need some background either in structural mechanics or in linear mappings to understand the material. If you come from the structural side, that's great. You'll have a lot of intuition about the structural system. If you come from the mathematical side, that's fine too. Then you'll have some feeling for how vector quantities are mapped into other vectors. Certainly our level here is introductory. I want to treat finite elements from ground up. So my intent is not to present theory too quickly, but rather to build slowly. Our main topic is linear static structural analysis. So what does that really mean? Here we have a curve of cause and effect where a line is given as typically an equilibrium position, and a system often will start at the origin and proceed under a cause out along this line. We're basically interested in the linear portion of that relation. Could be both positive and negative, such that our system moves up and down this line. That's called a linear system. Now, structural systems, in fact, if loaded enough, will encounter what might be called a softening effect here, and then possibly a jump phenomena where the system might leap from one static position to another static position. You can also get bifurcations where the solution branch will suddenly split into several arms. Now, these more exotic topics are beyond our scope in this course, so don't worry about those. We're going to look only at the linear case. Let me give a short personal introduction. My doctorate was from Caltech in July 1962. The degree was in aeronautics. We did have many classes and seminars in common with mechanical engineering and engineering mechanics people. My master's was at Iowa State, as was my bachelor's degree, both in aero engineering. Back then it was called aeronautical engineering. The space side hadn't started. Full-time jobs, well, after graduation I went to Wright-Patterson Air Force Base as a first lieutenant and did research at the Aerospace Research Laboratories. Then I came to the University of Michigan as a professor, and I've been here ever since. Sometimes I like to say I could never find honest work, so I became a professor. But it has been a pretty rewarding career, and working with young people is a challenge, and it's rewarding. I've been fortunate to have some contact with industry during these years of my own education and then the university professorship. When I was an undergraduate, I was able to work at Chance Vought Aircraft in Dallas for 3 summers, and that was a nice experience working with the F-7U, F-8U, and some wind tunnel testing. At the Boeing Airplane Company in 1957, I worked on the B-70 proposal. Since coming to the University of Michigan, I've had a fair amount of contact with the big 3 automakers and Caterpillar. My consulting company has done quite a bit of work with these companies also. And my biggest interest has indeed been the formation of a consulting company in Ann Arbor. You might call it a spin-off company from the university. It's called Automated Analysis Corporation. We currently have about 120 consultants located in Ann Arbor, Illinois, and North Carolina. We have a Peoria office and a Raleigh, North Carolina office. Let me finish with a few comments about hobbies that I love to play volleyball, both indoor and sand volleyball, and I've taken up downhill skiing this past year and a half, which I really love. So I've had a lot of fun in sports. Prior to that, I had done quite a bit of model building and gardening and woodworking, and I still like to do those as time permits. It's important for us to have a definition of what a finite element is out in front of us, and we can haggle about that and change the emphasis as time goes on, but here's a practical working definition for now. Let's consider that a finite element is a hypothetical subdivision of a structure or a system, and that subdivision possesses a regular shape that can be analyzed. Now, the point here is that the regular shape means that you can isolate a triangle or a quadrilateral or a hexagon or a hexahedron, and you can go off to the side and do lots of fancy mathematics to understand that element. Then later on, that information can be brought back up to the system level. Now, I've tried to show that as a process here below with 4 steps, so that the finite element method requires these steps. First of all, the development of the individual element. And this often uses classical mechanics, so we don't back away from the classical people, the Timoshenkos and Eulers and Bernoullis and so on. We indeed need their classical work. Then once you have elements, you have to be able to assemble them into your total structure or system. Thirdly, you have to be able to solve that assembled set of equations, and this depends very much on modern numerical methods. You really need to have efficient solvers. The dominant one in our static area is the Gauss elimination. This may change in time, but one such method of solution is dominating at present. Lastly, when you have your displacement field for the structure as a whole, you need to recover internal field variables such as stress and strain. And that recovery, in the way that we do this process, is actually an afterthought. It's uncoupled from the solution process, which is done in terms of the displacements at the points of interest. Well, what are these finite elements? I'd like to show you some sketches of a few simple finite elements, and we can talk about some of the details. First of all, there's the line element. The one I'm showing has 2 points of interest at its ends. Those are called nodes or grids. The node points are useful for a number of purposes. One is to connect to neighboring elements. The second reason is that you need to put information in and get information out of the element, and the nodes are the points of highest interest. Thirdly, you can use these nodes for accuracy because they provide degrees of freedom that characterize the field variable that you're interested in. And when I say field, I mean something like a displacement field, a stress field, or a temperature field. It doesn't mean anything really fancy. It's just a function of space. Now, on this latter question of getting accuracy, it's possible to add internal nodes. And this is done to some extent, especially on solids. It's done to a lesser extent on elements such as the line element. In fact, I don't know of a three-noded line element in the codes that I have been using. So there's always a trade then between adding more nodes internally with merely using a finer so-called mesh where you have smaller elements and more of them. And there is quite a bit of interest technically in this topic and a lot of research then as to which is better, to have these elements with more internal nodes or to have more simple elements. Well, let's go on to a two-dimensional body here. I show in this case what might be a planar element, or it could be curved and therefore be representing shells. Now you might have 3 or 4 nodes at the corners, and you can see how these would again attach to neighboring elements. This time you can have mid-side nodes that are more meaningful because they would be used in the attachment to the neighboring elements. Truly interior nodes can also be used. Let's stop for a moment and look at the displacement fields that are present in and at the nodes of these elements. In the top part of my figure, I show a line element again, or a rod element. Now, a civil engineer might call this a truss. With the 2 nodes at the ends, you have the possibility of a displacement being defined there that is purely a nodal displacement. Likewise, there will be the possibility of a force to be put in at that point or reacted. Now, those are nodal quantities, and I think people would have a pretty good feeling for that. And were there an internal node, we would also have a corresponding force and displacement there. Notice that the pair, the force and displacement, have the same sign convention, and furthermore, their product is work or energy. So we're very consistent on this with our nodal quantities in the finite element method. Now, beyond the nodal displacements, though, when this body is deformed, and let's suppose it moves now to a different point, and I will come up with a little different pen color here and show this body moving farther to the right, where it will take this position. And the point is that a material particle in the original undeformed position is going to now displace to a deformed position. I'll use a blue arrow for that. So that at some general point x, then, you will have a field quantity u of x. So it's a problem in finite elements then to find the field variable and describe it in terms of these nodal quantities at the periphery of the element. And you can see that this becomes a problem of interpolation. And that is the dominant side of all of finite elements. Now down below, I'm showing a planar body here, perhaps a plate element with 4 nodes, and this time I've shown you the displacements at the nodes. Again, the problem would be to interpolate and find what happens to a physical point in the undeformed body and where does that move in the deformed body. Again, you're going to have a displacement field with both u components and v components in this case, both as functions of x and y. So again, we need to interpolate in the interior of the element, knowing something about what's happening around the edges at the nodes. Solid elements are also very important nowadays, and there's more and more solid modeling being done of components such as forgings and castings. Here's a hexahedron element which has 20 nodes. It has mid-side nodes shown in red as well as the corner nodes. With such elements you can rather well define a circular hole, for instance, because you can make the 3 node points line up nicely with the edge of the hole. Other such solid elements are the tetrahedra elements that are becoming more and more popular, especially with automatic mesh generation. And then there are wedge elements that are degenerate hexahedra. The tetrahedra probably is the wave of the future because it's so much easier to fill a volume with those little four-sided pyramidal elements. Let's review the history of the finite element development. Williamson gives a nice paper which I list on the title page for this lecture. Leibniz in 1696 did a one-dimensional finite element problem, finding the elevation of a curved surface that provides the path of fastest descent for a frictionless block sliding on that frictionless surface. Shellbach in 1851 went further and solved a two-dimensional problem. It's really a soap film problem where he minimized the surface area of a film that connected in the interior of a closed wire loop. Richard Krant in 1943, in the war years, studied the torsion of circular shafts with cutouts for the propeller shaft of either an airplane or a ship, and he developed a small triangular element in torsion. Argyros in Europe did a lot of work in the early 50s and did discover many of the principles of finite element methods. One of the most important papers in finite elements seems to be the one by Turner, Martin, Clough, and Top in 1956. They developed a plane stress triangle and a rectangle that were needed in the aerospace industry, and that had really an earth-shaking effect. It really created an avalanche of technology. Within several years, the aerospace industry became completely turned over to what is now called finite element methods. Here's the problem that Leibniz worked on. The distance between point A and point P here is to be contoured such that a body sliding down this plane in this direction would reach the bottom in the least amount of time. Of course, it could be steep at first, building up great speed, but then there would be a long flat region to traverse if that were done. Or conversely, if it was merely a straight line path, then you would spend too much time in the early parts before speed was built up. So there's an optimum curve here. Leibniz was able to pick a point on that curve, and then viewing that as a function of the coordinate below, let's say that there's an x coordinate, then basically you're trying to find a surface position or a function of x, and that was done in a discrete way then by considering these small straight line segments. Leibniz was successful in developing the nonlinear equation for the brachistochrone, which pleased the mathematicians greatly. Let's look at the minimum surface problem that Shellbach studied. Here's a wire loop, and then in the region in between is stretched a membrane, and that will tend to achieve a minimum surface area in nature, for instance a soap film. This can be projected down onto the XY plane to show a pattern below. So Shellbach projected down onto the XY plane and imagined the projection of those triangular surface elements. He laid out a mesh as shown here and subdivided it into these right triangles. Interestingly, he only calculated the area of half of the triangles and then multiplied by 2. That sounds like that'd probably work. And he again was successful in getting the differential equation that described the surface. He had to do this in a limiting sort of way, a limiting process. The various engineering professions have adopted finite elements at different times as standard engineering practice. Aerospace structures people probably were first, followed closely by civil engineering engineers. Those two disciplines actually treat finite elements differently in that the aerospace structures people held it more proprietarily and didn't distribute their software widely, whereas civil engineers did a lot of public promotion of the method through textbooks and through university-developed codes. Nuclear engineers have always been interested in better piping and valving analysis. They have to build structures that last a long time. Naval architects use finite elements a lot in their hull structures. Their primary structure is a stiffened sheet metal structure typically. Zienkiewicz did a lot of work in engineering science areas and got people to use finite elements in problems like fluids in estuaries, finding the liquid line, say, in an earthen dam, the so-called phreatic line where the soil is wet. Mechanical engineers were a little bit later to come in, and I think because their methods were already sufficient for them. They had many table lookup methods and stress concentration factors and a lot of classical analysis that was sufficient. But one thing that has driven everyone toward using finite elements is the need to model an entire vehicle made of many different components and, in our terms, of different elements. So finite elements now is used widely for modeling entire automobiles. Electrical engineers have used finite elements to study field variables within semiconductors and within radar circuits. Lastly, aerospace fluids people were one of the last groups to come in heavily into finite elements. I've been told, and I can't really confirm this, that the biggest hang-up has been discontinuities such as shock waves and liquid-solid interfaces. There's an old engineer's rule of thumb that finite differences are better for that problem or for those two problems. I can't confirm that. Many serious finite element people say no, there's no fundamental reason why there should be any difference. One reason we like finite elements is that we can build the physics of the problem in at the element level, and so that each element has a nice physical interpretation which will conserve equilibrium and energies of various kinds. So I think it will emerge more and more as the fluid standard also. I'd like to give 3 examples of projects that I have worked on just so that the viewer has some feeling for what a typical finite element project might be. The first one was an all-welded load ramp. This is a bridge-like body about 6 meters long and 2 meters wide. Forklift trucks carry heavy loads on this from ground up to a rail car or to a truck. The body's made from cross members here that are I-beams and then sidewalls that are sheet metal with stiffeners at the top and bottom. There are end plates that are slightly corrugated so as to give some traction. They have a pattern embossed in them. There's a grating that lays over the I-beam bed, and I don't regard that as primary structure, so I leave it off in the analysis phase. Overall then, the stresses and deflections were found, and the goal was to use the finite element model for two separate geometries to validate a more conventional classical solution for stresses in the beams and plates. And that was done, and ultimately the load ramp was shown to satisfy a government criterion for loading, wherein a large billet of steel was placed on end at several critical points on the bed. A model that required solid elements was that of a load cell. This is a 50,000-pound load cell used by the Highway Commission in the United States under the platforms that weigh trucks. This was just a proposed design. It's basically a hollow tube that has been milled flat on two sides and then with cuts made to make a more sensitive area in the interior. The question is, how does the stress flow around these cut holes, and where would a person put the strain gauge to measure strain in this sensitive region? For instance, you might want to align the strain gauge in a direction where strain was largely constant along its length so that it wasn't averaging in that direction. The interesting thing that came from this was that there were very high stress regions around the holes, and I took this as a student project at the university for my master's level class, and we tried various hole patterns and undercut patterns here, and we really could never get the stress down low enough to satisfy their requirement that this not go nonlinear. The original design had a stress over 100,000 psi in the neighborhood of that relief hole, and at that point the customer decided to hire finite element people and replace quite a bit of their photoelasticity and really look at this, because it turned out to be a more difficult design problem than they had thought, and three-dimensional photoelasticity was taking so long to do. An interesting comment about the finite element model is that this body has what is called cyclic symmetry, and that was not available in the code that I used at the time. I used a code called Superb by Structural Dynamics Research Corporation. Since then it has not been put on the market standing alone, but I presume parts of it are built into some of SDRC's other products. It was a nice isoparametric element program in its day. Now, the cyclic symmetry I'm talking about means that if you look at an axis centered at this body and going into the plane of the paper, you would find there's a kind of a rotary symmetry here where you could take the bottom half of the body and rotate it about that axis and get the top half. So the code that I used couldn't exploit that. It didn't have what were called multi-point constraints. You see, what's going to happen on this part of the boundary on this side is going to be actually perhaps a negative of what happens on the other side, or at least a reflection rotated 180 degrees. And so there is a way to handle this in some modern codes that have what's called cyclic symmetry. And in that case, you could get by with modeling only half of the body. But I couldn't do it at the time, and I overran on my computer money as a result. A third project of interest is an aircraft trailing a long cable, which could either be an antenna or a way of carrying goods at the end of the cable in a capsule. This was the thesis work of John Russell, an Air Force officer who recently retired as a colonel in the Air Force. Here the cable is shown trailing in a sort of a helical shape such that the capsule at the end rotates in a circle about the axis. If the plane maneuvers properly at the right speed and radius of orbit, you can make this capsule rotate in a relatively small radius about the axis. The principle was originally figured out by Nate Saint, who was a missionary in South America. And I remember seeing in the National Geographic a picture of his Piper Cub in the distance trailing a 500-foot-long rope. Natives in a clearing were reaching up and grabbing the basket at the end of the rope, which was hanging almost motionless. really oscillating in a small circle. So that was an experimentally developed technique. Unfortunately for Nate, the Indians later captured him and killed him. So I guess, boy, if people in finite element analysis have trouble with their customers, why, he really was the extreme case. So at least our customers usually don't kill us after a project. But in this case, we modeled the cable with 10 elements, which proved to be sufficient. We were able to predict several instabilities. There was a flutter instability, a jump instability. This indeed was a nonlinear problem in the geometric sense that the cable could move through large angles. And so a homemade code was developed to handle this case. So the three examples that I've mentioned here have used, in the first case, a university-developed code for the load ramp called SAP. In the second case, an industrial code called Superb. And then in this third case, a homemade program made at the University of Michigan by a graduate student. Here are some lists of commercial codes that will help the viewer understand what's available. In the United States, structural finite element programs can be partially divided according to purpose. I've made the first 5 codes here in one group because they're all Nastran and Nastran derivatives. The original government-sponsored code was Nastran itself and still can be obtained from the U.S. government. MSC Nastran is perhaps one of the most popular and most widely used codes in the world. CSA, Astros, and UAI Nastran are other versions. Astros is being developed at Wright-Patterson Air Force Base and has some aeroelastic optimization in it, makes it a little unique. ANSYS itself is also very widely used, in contention for one of the most widely used in the world. Abacus and Mark are 2 nonlinear codes. You can actually do very nonlinear problems such as blowing of glass and closing of seals. In my consulting company, I know there are several people that work on rubber seals and use Mark because of the ability to follow the contact surface through large change. I'll continue with the list. Algor and Cosmos are programs that have become known for installation on PCs, personal computers. There are 3 codes that are widely known because of their graphics capabilities as well as their finite element solvers. Ideas and Patran have become pretty much the industry standard for modeling purposes in pre-processing and post-processing. Then I've only clustered the remaining codes alphabetically, merely for my convenience. These are different codes in many different ways. Adena is a strongly nonlinear code. Mechanica is a so-called P-convergent code, and we'll discuss convergence later on. The SAP series were really widely used in universities and in industry. They have survived partially through these smaller codes that are still being used. Strudel is an MIT civil engineering code. Stardyne was one of the oldest codes and still in use. Now there are also a large number of European developed finite element codes. Here I've listed them in alphabetical order. These are companies that often advertise in the open literature, such as in John Robinson's magazine, Finite Element News. So I know that I have missed some codes and I'm apologetic. I would like the vendors, if their code is a major one selling $1 million or more a year, I'd certainly like to include that in future versions of this list. The next figure completes the European developed finite element codes. The last figure with lists of computer programs has to do with boundary elements and then fluid finite elements. These are both a little bit on the fringe of our topics in this course. Boundary element codes are those that use elements only defined on the boundary and not in the interior of a body. Boundary elements follow a different theory. These elements cause a perturbation in the continuum that is felt at a large distance. You can save labor by using these codes because for solid bodies, for instance, you only need to mesh the surface of the body and you don't need to mesh the interior. The limitations, however, are that it's primarily a linear type of analysis. Some extension is being made, however, in the contact area, and the codes can be upgraded to consider contact. Then the fluid finite element programs. Here's where several new fluid codes are being developed rapidly at present for flow around bodies such as automobiles. The code rampant is being used quite a bit by a research group that I'm working with on underhood flow. So the finite element approach seems to be emerging in fluids in spite of the fact that it has been slow in coming. While preparing these lectures, my son Glenn and I have started doing what are called morphs, and this is the gradual blending of one body into an image of another body. And you've seen some of these things in the Terminator movies, and where a normal person will turn into somebody made out of stainless steel or something. That'd spoil your whole day probably. But we've done the same thing with myself and my daughter here just for the fun. And so the question I'm answering in this first figure is, have I been spending too much time studying finite elements? And you can see the progression from me, from a normal me into a finite element. It looks a little bit like a bag put over my head. Of course, the answer is probably yes. I should probably be sticking to skiing and playing volleyball by now. But anyway, it's kind of fun to do this. And you know how it's done. You'll take the image of the person at the top and then some other object, either another person or an inanimate object, and then the program will allow you to match points, maybe the tip of the nose on the person with the tip of this sketch. And then a linear mapping is done in which you take certain proportions of each of those figures. The 50% proportion is shown here at the right, so that's half me, half finite element. Probably the way my wife thinks I am most of the time anyway. My daughter Ellen was walking by when we happened to be tinkering with this, and so my son captured her and got a photograph on a video camera, and then with a handy stick of broccoli we converted Ellen into a stick of broccoli here. And again the question, has Ellen been eating too much broccoli? Well, I don't know. George Bush wouldn't do it, so somebody had to do it. And I suppose that would have been a better morph yet, would have been taking George Bush's figure and converting it into a stalk of broccoli. Well, that ends our first lecture, and at this point we're going to turn toward more technical topics, and we'll start with the rod element next.